Hello everyone, it's a recorded lecture for you people so that you can watch since you might have your exams. So you can watch it later as well. So I just record the video for you people. So today we are going to solve the problem related to motions of charged particle and it's a concept from electromagnetic theory. So we will start the today's lecture. So I think you are all familiar with these pictures of charged particles when they are in case placed in electric field. For example, here the electric field is created by some test charge Q and you place another charges Q1, Q2, Q3 in an electric field. And now you know if you wanted to calculate what is the force that is experienced by these charges, you can generally use electrostatic picture and the formula is given by Q1, Q2 upon R square for pi epsilon naught into R square. So you can use that picture directly to calculate the forces that is acting on your charged particle. But when the charges are in uniform motion, they will generate the current. For example, if you have charges which are flowing from this plus charge part of the battery to this negative part, so charges are moving through the circuit, and the current is going through that. And now you can see that the field is neutral in the sense if you place another charge here, it will not going to experience any force. However, there is a field created by this motion of charges, and it is the magnetic field. And if you place another wire which carry opposite or in the same direction the current flowing, then these two experience a force of attraction or repulsion among them. And this leads to a concept of magnetic forces and it arises due to the magnetic field and which is generated by the moving charges. And you're familiar with that the direction of magnetic field is given by this right hand thumb rule. You can just take your wire and you just enclose it in your fingers and then your thumb will give you the direction of magnetic field in the direction of thumb and then your fingers will give the direction of magnetic field. And now what happens if you place a charge in a magnetic field? You have seen that if your current is flowing in a wire and you place another charge Q here, then it will not going to experience any force as long as it is an static situation. But if it is moving some velocity v means that means there is some charge current is flowing due to the motion of the charge and that current is going to experience a magnetic force. So magnetic force is only experienced when the charge is moving and it is placed in a magnetic field. Hello, actually I am thinking of recording the video for you people. So if you want I can even start it again. Uh, Hello, are you listening? Am I audible?
Yes, ma'am.
तो मैं ऐसे रिकॉर्ड कर रही थी क्योंकि कोई स्टूडेंट आया नहीं था बट इफ यू वांट आई कैन स्टार्ट इट अगेन.
No, ma'am. Continue.
Okay, so just what we are doing is today we are going to learn this concept of motion of charged particle. So basically we are going to learn how different charged particle is going to behave if they place in different kind of field. Like if we have charged particle, they are placed in an electric field which is created by another charge, then they are going to experience the electrostatic force. But if they are placed in a magnetic field which is created by moving of charges, then they are going to experience magnetic force if they are moving. If they are in a static situation, they are not moving, then there will be no experience of magnetic force. And the magnetic force can also be experienced if we place another wire near to the wire which carry current. And depending on the direction of current flowing between two wires, the force may be repulsion or attraction between these two wires. So this is the case when magnetic field is there and you are familiar with that the magnetic field can be calculated by using this thumb rule, the direction of magnetic field. And now if we place a charge q near to in a magnetic field, it will not going to experience any force. So for a charge to experience a force, it has to be moving. And this is given by this formula, Lorentz law. The magnetic field created by experienced by a moving charge is given by q p cross p. So if v is zero, that means charge is not moving. It will not going to experience any force, and the force is going to be applied only on the component of velocity which is perpendicular to this magnetic field. If the parallel component will give cross product zero. And also the magnetic field is perpendicular to both V and B. This is the property of cross product itself. And now if along with the magnetic field you have the electric field as well, in that case the force is given by QE plus QV cross B. Force due to electric field, force due to magnetic field. So this is the Lorentz law. And there is this cyclotron principle in which what we do is we have the magnetic field which is like perpendicular to the plane of paper, and in this magnetic field we have shoot a charge v with a velocity vector which is perpendicular to the direction of field. So we have to calculate what is the kind of force the charge is going to experience. And it is known that if a velocity component is perpendicular to this magnetic field, then it will start in circular motion. And since circular motion is accompanied by this centripetal force, so the centripetal force and this force which is created by this magnetic field, they are going to compensate each other. And from there, we can calculate what is the radius of the circular motion of the particle. So force due to magnetic field is given by QV cross P. And since V is perpendicular to magnetic field, so we can write QVB sine 90. So it will become QVB. And now force due to centripetal force is given by mv squared by r. So we just take these two components equal. From there, we calculate the radius of magnetic field. But if your particle will have both the component one which is parallel to the motion and perpendicular to the motion, in that case, what will happen if it will move circular because of perpendicular component of velocity, but the parallel component of velocity will move in the direction of magnetic field. So it will move like this. So this kind of motion is known as helical motion. This motion is due to parallel component of velocity. Um, this will not, this will not work in this case because parallel component of velocity in case of magnetic field will just simply moving the particle. Okay, so there is also this concept of like if you place a particle which is perpendicular to the magnetic field, then it just start moving in circular motion. And if a particle is moving in circular motion, that means current is generated in circular motion. And whenever you have a current carrying loop, there is a magnetic moment. So what is the magnetic moment? Which is generated by the motion of this charged particle. So we can calculate this from the formula that magnetic moment is given by current into I, current I into area of the loop which is created by these particle motions. And since area is given by pi r square and radius we have already calculated initially, how to calculate using motion. So from that we can calculate the area. I is given by charge per unit time. The charge is the charge of electron which is moving, and time can be written as 2 pi by into omega. So we can write q as not 2 pi by omega. Here time can also be calculated like angular velocity is given by v by r, and time is 2 pi by omega. So from there we can calculate omega is qb. So 2 pi by qb into m. We can put the value of this time factor here. From there, we calculate the magnetic moment as I into area and then put the value of R. So this is the magnetic moment of this charge motion when it is moving circular motion due to this magnetic field. Now what happens if we place a charged particle inside an electric field? So in case of electric field, the charged particle is moving in the direction of electric field. So if you have an electric field and you place another charge, then it will start moving in this direction or opposite to direction depending on the sign of this charge. And we can simply write the force ME equals to QE and to integrate this equation, apply the initial condition that initial velocity is V0 and position is R0. So we just integrate it and it will tell you how your particle is moving as a function of electric field if you apply it onto them. So there will be no motion perpendicular to the electric field as in case of magnetic field. Either the particle is moving the direction or it is moving in opposite direction depending on their charges. And what happens if we have both the electric field and magnetic field as well? So in that case, what is happening? Your magnetic field lead to circular motion, but it is going to work only when particle is moving. Electric field can be act on a particle at rest. So for example, at zero origin, your particle is at rest, and due to electric field, it is start moving in this direction. And as it speed up, and the velocity is increasing, and so magnetic field start applying on them, and it will try to move the particle in circular direction. Since this kind of motion, the circular motion opposes the motion due to electric field, therefore particle velocity start decreasing and at some time it will become again at rest. Again the electric field take up the velocity and the magnetic field bring it back. So kind of because of these two opposite motions, the particle motion will become cycloid and we can prove mathematically that the motion is cycloid as well. For example, if we take the magnetic field in x direction and electric field in z direction, so a positive charge is started from the origin, and what will be the path it will follow. So we simply write the equation of motion force ma equals to the QE plus V cross P, and there is no force in x direction. The force due to the magnetic field is given by QV cross P. So it is perpendicular to both V as well as P. So there is no motion in this x direction. So we can describe our velocity as 0 in x direction, y dot in y, z dot in z direction. Similarly, position y as a function of t in y direction and z direction. There is no displacement in x direction. Then we can calculate the curl v cross b. This will become this. And now we will put all these equations into first. So this is dv by dt for differentiation twice. And we just equate the y component and z component here. Now by equating the y and z component, we are ended up having equation like d2y by dt square equals to qb by m into dz by dt. Kind of coupled equation. So if we put qb by m, we are ended up having this type of coupled equation. And if we solve this equation like by differentiation, this one more time and this one more time and replace these values inside them, then we are ended up having the solution which is like C1 cos omega t sine and cosine equation. Now again using the initial condition that at origin the velocity is zero and distance is also zero, we can see that the value of y and z is kind of forming a cycloid. Sine omega t, this kind of parametric equation is a equation of cycloid. And if we can further simplify by putting E by dv by dt, we can write the circular motion. and with radius r in the z and r omega t in the y. So your radius is kind of moving continuously in y direction with a constant in r direction. So r is the constant in z and it is moving with r omega t in y. So this is kind of cycloid motion and your speed is given by E by B. But if you are given some another kind of field, you can use the direct formula for to calculate this velocity drift velocity as E cross B by B square. So you do not have to do all this complete derivation. You can directly use this formula as well. The derivation is just to tell you how to do calculations. If we are given two different type of field and you have to calculate what kind of motion the particle is going to perform. Just calculate the force due to those field and put into equation of motion. Solve the differential equation. You will get this android. Now we will solve certain questions from the GATE exams. And this question was asked on Telegram by some student. So a particle is moving with a charge q and momentum t in a horizontal plane under the action of uniform magnetic field. So your charged particle is moving in a kind of circular direction due to this magnetic field, and they have made the measurement on particle trajectory, but the answer is given in terms of sagittal, which is the distance of this chord of length L and this radius circular motion surface. So we have to find out which answer is correct. We know that the particle momentum is given by QRB, but we have to write this radius in term of this factor S and L. And I think you are familiar with that. If you have some sort of curve, then if the radius is not passing through the center, if the curve is not line is not passing through the center, this is known as chord. And if it is passing through the center, this is known as diameter. And there is this distance sagittal, which is the radius, which is the distance of this chord from this surface. So we have to find out this answer in terms of these two values, S and L. But this is formula that is given in curve that if you are known the radius, if you wanted to find out the radius, you can use this formula directly between the relation between S and L. It is given that S is much less than L. So we can use this here by taking S out. Our this quantity will become very small. So we can neglect this quantity. No, this quantity become very large. S by L, the opposite of that will become very small and L by L will become very large. If you take it like this. So from that we can neglect 1 and our R will become L square by 2s. From there momentum will become QB L square by 2s. So that will become your correct answer. Okay, so that was the question from GATE 2014. The value of magnetic field required to maintain non-relativistic protons of energy 1 mega electron volt in a circular orbit of radius 100 mm. So we have to find out what is the magnetic field. Energy is given to us for the case of protons. Since they are moving with the speed of light, so we can directly use the energy as p square by 2m. They are given that they are non-relativistic protons. So energy is the kinetic energy, which is p square by 2m, and p means momentum, which is given by QRP. R is given to us as 100 mm. D we have to find out, and Q is the charge of your proton. And energy is given to us as 1 mega electron volt. We put all this value in these expressions, and this is our magnetic field, 1.44 Tesla. So all the questions from this topic is going to be very simple. We have just to remember that the momentum, we have to remember only one formula. Most of the time, this will make our life quite easy. Radius is given by mv by qb, and this v has to be perpendicular component only. Parallel component will give you the pitch of this helix. that we have calculated. Yeah, P cross B. Okay, so there is another type of question that was asked from GATE exam also. Like we have calculated the magnetic moment which is created by the movement motion of one electron. Similarly, we may have the charge distributions as well, and it is moving with velocity omega, angular velocity omega. So what is the magnetic moment in that case? So if your charge distribution is around a ring, so this condition and a single charge is moving in circular motion, they are both same. So in that case, magnetic moment is going to be same. Basically, you have to calculate I into A. I is given by charge by time. So charge is Q, time is 2 pi by omega. So we just put the value of I into A, which is pi r square. So this will become your magnetic moment. Now we have to calculate what is the magnetic moment of this. The difference between previous structure and this one is now your charge is distributed across a whole surface. So what we do is to calculate the magnetic moment of this disk, we just take a small ring and calculate. We have already calculated the magnetic moment of this ring, and if we integrate this ring over the complete radius, then we are able to get the magnetic moment of a disk. The same kind of thing you have done in moment of inertia also. So basically, magnetic moment is given by 1 by 2 q omega r square for the ring. So we have to just calculate I into A again for the case of this. R is given by Q upon T. So we will calculate charge per unit area for the disk. Since we are given a charge distribution across a surface by sigma, so charge per unit area is given by Q upon pi r square. This is our sigma for the case of disk. And now area of ring is, you just take it this distance to pi r into multiply by dr. See, if you take this ring and take it out, it will become like this. So total length is given by the circumference to pi r and its width is given by dr. So the area of this ring is 2 pi r into dr. So charge on ring dq is given by q upon pi r square, which is the complete charge per unit area multiplied by area of ring. So magnetic moment is given by charge q. We just use directly the formula for ring. So replace dq by the charge on this ring and integrate it with respect to r. So from there we will calculate that the magnetic moment of this is given by 1 by 4 q omega r square. So basically in all these kind of problem, we just have to find out how the charge is distributed, like the mass is distributed in case of moment of inertia, and calculate this moment of magnetic moment. For example, in case of magnetic moment of a sphere, we have this volume. So we just take a disk here. So you can think of this sphere is formed by these small disks joining together. So we just take one disk here, and the disk moment, magnetic moment is q omega r square. So in case of sphere, we just take a disk and its its depth is taken as dx, and its radius is r, since it can be taken anywhere, and you can apply Pythagoras theorem to find the relation between r square plus x square equals to r square. So your disk is taking at a distance x with a small radius r, and from there we will calculate the charge per unit volume of this sphere and then calculate the volume of this disk. Since we know that its area is given by pi r square and its height is given by dx, so it will become the volume of this. And when you multiply this term, volume of this with volume of this charge per unit volume, you will get the charge on the disk. Then you will calculate the magnetic moment of the disk, which is already calculated. Q is replaced by dq here, and dq is given by this expression. And since this will become your magnetic moment of this disk. Now, if you see your r is square, but integration is with respect to x, so you replace your variable r using this formula. And as you can see, your x can change values from 0 to capital R here. Not x can change value from it here minus r to here, which is plus r. So just integrate your integration and you will get the magnetic moment of is there. Like this type of question asked in GATE 2019, in which we are given a solid cylinder of radius r and total charge q distributed uniformly over its volume. It is a rotating about its axis with an angular velocity omega. The magnitude of total magnetic moment of the cylinder is. Now we have given a cylinder, so we can think of this cylinder as a combination of small disks. And we know that the area of this is pi r square. This time r is fixed since it is of cylinder, but now their depth is varying. So we can think of this disk with area pi r square and depth dz. So the volume of our disk this time will become pi r square dz as a volume of disk, and volume of this cylinder is pi r square. Total length is, if we take it L, so the charge density of the cylinder will become Q upon volume of cylinder. So charge on disk is charge density of the cylinder multiplied by pi square dz. So the magnetic moment of the cylinder will become magnetic moment of this disk with Q is replaced by dq. dq is then taken this term and dz can integrate from 0 to L. Either you integrate from 0 to L or you integrate from minus L to L, L by 2 to L by 2. Both will give you same answer. So this will become your magnetic moment in case of cylinder 1 by 4 q mega square. So this was the questions from GATE exams. So if you have any doubt, you can ask. Otherwise, we will finish the class. Or if there is some another thing that you want me to cover in next class, maybe next class will be the last one. So just let me know. When is
Ma'am,
your GATE? Yes. Hello.
hello.
Huh.
Ma'am, do you have 2014 question paper?
Question paper.
I was
Yes.
I was having some doubt in the question.
Abhi question paper. I will
Uh,
search it. So which question?
36th, ma'am.
This one.
Uh-huh. Ma'am, I
This.
would just means I didn't get that how can a light which goes from a rarer medium to a denser medium will bend towards normal, right? But here it is bending away from the normal, so I didn't get that point.
But it is not given कि हमारी light it is going from rare to denser. They are just
Ma'am,
given that.
answer is coming like that. E2 is coming greater than E1.
Okay. But I think they have said in the question that your ray is going like that and it is become then parallel.
Yeah, that's what I was saying. Means, if we consider the medium one as a big sphere, then it would become flat, right? So the normal
Mhm.
would be in the radial direction, and if it is going from rarer to denser medium, it should bend towards the normal.
It seems like it is bending away from the normal.
Yes, ma'am.
Where I don't consider the question from that. All we have to do is, meaning if you are given the refractive index, then you can consider in that direction, like your wave is going to be towards the normal or away from the normal. But this
Ma'am,
condition
if
is
we
not
apply the
true.
boundary conditions and all that things, no, then it's coming. Uh, it's in the second medium. It's coming denser.
Is it affecting your answer? Means if your theta will change here. Actually, I am not able to answer this question. Sorry.
Okay, ma'am.
Or any
Oh,
other doubt. ओके सो तुम्हारा एग्जाम शायद सैटरडे है ना 11th को.
हाँ.
ऑल द बेस्ट.
Thank you, ma'am.
ओके बाय बाय.
Thank you, ma'am.